We have seen Routh array, how to find the roots on the right hand side by using Routh array. Already we have seen. Today we are going to see how we can fix the value of k so that the system is stable. We have seen that if you increase open loop gain k, there will be a movement of closed loop poles. As k increases from third order onwards, the closed loop pole will move to the right hand side of S plane. That's why we have to fix the value of k for the system to be stable. That we will see today by using Routh-Hurwitz criterion. This is what we are going to see today. For each of the characteristic equation means what? Denominator polynomial of closed loop system. Then only we can call it as characteristic equation. Denominator polynomial of characteristic equation means denominator polynomial of closed loop system. Generally. Okay. Here, suppose I am having kg of s I am having. That is open loop transfer function. Open loop transfer function is kg of s, or g of s equal to k upon s square plus 2s plus 3. Let us assume what is closed loop transfer function. Let us assume this way: k upon s square plus 2s plus 2. T of s equal to T of s. Closed loop transfer function is what is unity feedback system. Unity feedback system means what is closed loop transfer function? Numerator divided by denominator plus numerator. That is equal to k upon s square plus 2s plus 3 plus k. Actually, in the open loop system, k is in the numerator. K is in the numerator. K is in the numerator. In the closed loop system, k becomes part of denominator. Suppose k is variable, means the roots are moving. The roots are moving. As k varies, the roots are moving. How many roots you will get? This is second order, 2 roots. Suppose k varies from 0 to infinity. How many roots you will get? 2 sets of infinite roots you will get. 2 sets of infinite roots you will get. Because as k varied from 0 to infinity, as k equal to 0, you will get one set of roots. K equal to 1, you will get another set of roots. K equal to 2, you will get another set of roots. So infinite number of roots you will get. That's why we have to fix k. Already I told you that from second order onwards, no problem. Up to second order, if it is open loop stable, means closed loop also stable. We'll study later about that. From third order onwards, if it is third order system, means as k increases, the poles will move towards right hand side. This is what is the order of the system here? Fourth order. Third order onwards, as k increases, roots will move to the right hand side. Therefore, we cannot increase gain of the system beyond a certain value. If we increase gain, the system becomes unstable. The system becomes unstable. That's why the speed is dangerous. No system in the world is first order. No system in the world is second order. More than second order, all systems. Your bike you are riding means your order is third order onwards. Maybe third order. If you increase gain means the poles, the left hand side will move very close to j omega axis. So if any disturbance comes, you will oscillate. You can notice when the speed is very high, you cannot take decision. It will oscillate because the poles are very close to j omega axis. That's why speed is dangerous. Here, for what value of k, the poles are on the j omega axis, we can find by using Routh-Hurwitz. That we are going to find. What is the question now? The range of k for stability. I told you that the poles will move towards right hand side. Suppose this is a third order system. As k increases from 0 to infinity, this pole moves towards left. This pole moves towards right. This also moves towards right. So here k equal to 0. Here k tends to infinity. As k move, k tends to infinity. Here, for a particular value of k, the poles will be here. The poles will be on the j omega axis. For a particular value of k, the poles will be on the j omega axis. That value is called k max. Maximum value of k, up to which the system is stable. Below k max, the system is stable. If it is equal to k max, marginally stable. Above k max, unstable. So that we can find by using Routh Hurwitz. That we are going to find. So the first sum is s power 4, s power 3, s square, s power 1, s power 0. The first row is 1, 25, 15, 20, k. Because they didn't give value. We have to find for what value of k the system is. Range of k for which it is stable, we have to find. Therefore, it is k. Now, s square you have to find. What is that? 25 multiplied by 15 minus 20. How much? 375 minus 20. 375 minus 20 equal to, am I correct? 375? Okay. My 355 divided by 25, 5, 71. So 71 among 5. Here k will come automatically. S power 1th row, 71 by 5 multiplied by 20 minus 25k among 71 by 5. So we can write 71 multiplied by 20, how much? This is 71 by 5. $1,420 minus 125k divided by 71. S power 0 is k. So what are the first row elements? I am writing again first row elements only. S power 4, s cube, s square, s power 1, s power 0. First row elements are 1, 25, 71 bar 5, 1420 minus 125 k upon 71 k. So these are all must be positive for a stable system. These are all must be positive for a stable system. If all these elements are positive, it means what is the first condition? K must be greater than 0. K must be greater than 0. First condition. From s power 0th row, we can say that k must be greater than 0. And one more condition, 1420 minus 125k should be greater than 0, or k should be less than 1420 divided by 125. K must be, so 1420 greater than 125k. Therefore, k must be how much? How much? 1420 upon 125, how much? 11.36. So, this, if k is greater than, if k is greater than 11.36, then only, sorry, if k is less than 11.36 and k is greater than 0, then only the poles will be left hand side. Otherwise, it will be on the right hand side. If it is equal to 11.36, poles will be exactly on the j omega axis. Poles will be exactly on the j omega axis. If it is exactly on 11.36, can you tell more decimal places? 11.36. Very good. So k should be the range of k. It is asked. Range of k is it should be less than 11.36 and it should be greater than 0. For 0 to 11.36, the system is stable. At k equal to 11.36, it is marginally stable. Marginally stable. Marginally stable. When at 11.36, if it is greater than 11.36, the system is unstable. Let us check all these things in MATLAB. So let us put 11.36 exactly and check. Tell me the coefficients. 1, 125, 15, 20, 20, k equal to 11.36. 11.36. We cannot, or we can enter k. That is also possible. We can vary k. That is also possible. K equal to 11.36. Now let us check the roots. 2 poles on the J omega axis. 2 poles on the J omega axis. So the closed loop system, it becomes marginally stable for 11.36. Let us check for k equal to 11. Let us check k equal to 11. 11 k equal to we have to run this one time. We have to run this one time. Now we can find the roots. All poles in the left hand side. All poles in the left hand side. Now let us check the simulation of what happens when k equal to 11.36. K equal to 11.36 transfer function. Numerator. Is it the transfer function? K equal to 11.36 and we have to run one time. We have to find the transfer function. Okay, 11 numerator whatever. 11.36. Transfer function is 11.36 s power 4 plus 25 s cube plus 15 s square plus 25 s 11.36. So for this, let us check the response. Impulse response of C. Sustained oscillation. Sustained, no change in amplitude. Remains oscillating up to 800. Let us give less than 11. Less than 11. K equal to 11. 11 point, less than 11.36. What happens? Let us check. We have to run numerator. It becomes 11. Denominator also we have to run. Now we have to find the transfer function. transfer function. Now, K value is less than 11.36. Now, what happens to impulse response? Oscillating and finally settle. Oscillating and finally settle. Here, when 70, this row, S power 1 row will become 0 when K equal to 11.36. Therefore, we have to consider S square row. S square row is what? S square row is 71. S square row is 71 by 5 S square plus 11.36 equal to 0, or 71 bar 5 S square equal to minus 11.36, or S square equal to minus 11.36 multiplied by 5 divided by 71. Therefore, S equal to plus or minus J square root of 11.36 multiplied by 5 upon 71. That is equal to plus or minus J 0.894. The frequency of oscillation is 0.894 for the first sum. For what value of K, the system is marginally stable. And find the frequency of sustained oscillation. To find frequency of sustained oscillation, what we have to do is make S power 1 row 0. For that, what is the value of K? You have to find. So you will get a row of 0. If you make S1 row equal to 0 means a row of 0. So consider the auxiliary equation S square row, find omega. That's all. That is the procedure to find poles on the J omega axis. Poles on the J omega axis. The omega value is 0.894.